Hello, my name is Marco Roberto Cavallari, and I will present to you the work entitled Cross-linked polyvinyl phenol in thin film transistors for water analysis. This work is a collaboration between the University of São Paulo and the University for Latin America Integration. So, there are around 1 million inhabitants in the surrounding of Guarapiranga Dam in São Paulo. That creates a problem for the city, right? So we get an excess supply of nutrients due to the large amount of sewage discharged in the dam. More than that, there is trash in those waters and also a lot of people that go inside for recreation. Just remember that these waters are later supplied to the city. Okay, so as a consequence, we get eutrophication, which can be translated as an abnormal proliferation of algae. We can see in this picture a duck that became green after entering these waters. Finally, the problem is that algal decomposition releases compounds that give water a bad taste and bad odor. Okay, so the basic sanitation company of the state of São Paulo has to solve this problem, right? So it needs to detect methyl isobornyl or geosmin, which are related to this bad taste and bad odor of the water. In this work, we are targeting methyl isobornyl through isobornyl detection. The challenge faced by SABESP, in which this work is related, is predicting increased methyl isobornyl and geosmin levels, solving the complaints from more than 10 million people about bad smell and bad taste of water, and also sensing concentrations in the tens of nanograms per liter of these two compounds. So the device we chose to fabricate in order to detect isobornyl was the bottom gate, bottom contact organic thin film transistor, which is used as a gas sensor. In the presence of gas flowing through the semiconductor containing the isobornyl molecule, it should produce changes in the electric current flowing between source and drain. The challenges related to this structure are performing photolithography of metal source and drain on top of the dielectric, which is gray here, and then performing semiconductor deposition, which is the violet semiconductor here, on top of the dielectric. So the dielectric needs to be chemically resistant in order for us to fabricate this device and then test its sensitivity to isobornyl. So let us see now in more details how the device is structured and fabricated. Initially, there is BK7 glass, on top of which we deposed and patterned gold gate electrodes. The gate dielectric is PVP, which is cross-linked with PMF. The cross-linking is necessary in order to pattern source and drain electrodes by photolithography and deposit the organic semiconductor, which is in this work PBTTT-C14. The organic structure of these molecules are shown here. Okay, so let us see now the photomask used for photolithography. The gate photomask is the first, which has this shape, since the source and drain electrodes are interdigitated. The mask has also 8 OTFTs from 4 to 20 micrometer channel length, and the channel length is the distance between the source and drain electrodes, as we will see. And the pads were placed on the border for a better electrical contact. There were also 8 capacitors with 500 to 2000 micrometer side in order to study just the organic dielectric. Finally, after the gate lithography, there is source and drain lithography. We can see in here that each electrode has a comb-shaped structure, being the channel length the distance between these two fingers, right? Also, in this case, the pads are placed on the border for better contacts. Thin films were studied by Fourier transform infrared spectroscopy and atomic force microscopy. And in this work, we're going to show results for the organic dielectric. Electrode devices such as transistors and capacitors had their current versus voltage and capacitance versus voltage curves extracted by keysight and metronome instruments in a micromanipulator. In order to extract gas sensing response, we used two rotameters, while one flowed pure nitrogen into the chambers, the other one was flowing through a bubbler carrying water and the contaminant, in this case isobornyl, into the chamber. Two different chambers were used because in one of them we placed chemical sensors, which were just composed of two electrodes and the organic semiconductor. And in the other one, there were the transistors and capacitors, right? Which were then investigated by LCR meters, in the case of chemical sensors, and keysight semiconductor parameter analyzer, in the case of transistors. Okay, so let's see now results for thin film characterization. Just as a reminder, the molecule of PVP is composed of a hydroxyl group, which presence tends to decrease when there is cross-linking with PMF. So in the case where there is no PMF, there is a strong presence of OH bands in the FTIR spectrum. By adding 5 times more PMF, we can see strong decrease, right, of these bands, which indicates the cross-linking of PVP with PMF. Atomic force microscopy is important in order to assess the roughness of the surface. In this case, pure PVP films had a roughness of around 0.3 nanometers, while after PMF addition, the roughness was also around 0.3, a little bit higher, but not higher than 0.4 nanometers for similar thicknesses. After showing that the device had gone through cross-linking and the roughness was low, we fabricated some capacitors. Devices at 1 to 0, that means pure PVP capacitors, did not work, so did not withstand photolithography. And we could observe that device with higher PMF ratio had higher dielectric constants, so high K devices, despite having a higher leakage current. However, this current was more uniform compared to devices with less PMF, and the breakdown voltage was also higher in this case. Okay, so after studying the capacitors, we studied the transistors, but also the chemical sensors. So it was observed that the resistance of PBTTT, which is the semiconductor film, it decreases after exposure to isobornyl, and this agrees well with an increase in mobility which is observed for transistors. But also in transistors there was a decrease in the threshold voltage. So the combined effect of these two parameters produced a decrease in device current. It is worth saying that sensitivity at 10 ppm is already at 20% for transistors, while it's less than 10% for chemical sensors. And it is worth also saying that the concentrations used here are much higher than real concentrations in real samples, right? So After 1 month, the device had been degraded, and this can be observed by the changing color from the semiconductor. Okay, so now the final conclusions. Cross-linked PVP made it possible to fabricate bottom gate, bottom contact transistors with fully photopattern electrodes. The cross-linked dielectric was processed at 175 degrees Celsius and 1 atm, which is compatible with some flexible substrates. The semiconductor, both in chemical sensors and transistors, proved to be sensitive to isobornyl at 1 volt, which is really a low voltage for organic devices. And finally, this was one more step towards an electronic nose for water quality monitoring in real time, which is our final goal. So thank you for your attention and feel free to ask questions.